So hello everybody and welcome back to another term and another action-packed seminar series with the GSI. So they're going to run much like they did in our sort of trials in the summer, which is basically just means you can ask questions in the chat, but keep your questions to the end if you want to ask them out loud. So today we have Mike Allen speaking, and he's going to be giving us a dive into his career and research. Mike is an associate professor of single-cell genomics in CLES, so the Exeter College of Environmental Sciences, but he's also a merit scientist at Plymouth Marine Laboratory and an honorary fellow of the School of Physics at the University of Bristol. So with that, I'm going to hand over to Mike, and he can tell us about fuel, feces, fertilizer, and fun. Take it away, Mike.
Cool. All right, thanks for that lovely intro. Nice to not see you all, I suppose. I'm just looking at the screen here. I thought I'd put together a few slides. It turns out there's quite a few slides here on some of the work that I've been doing over the last 10 to 15 years. So the title was basically to trick you all to come here and listen to me. And I apologize for the fuel, feces, fertilizer, and fun. Because of homeschooling and stuff, I've recently found what an alliteration was, so I wanted to show off, basically. But I didn't know what that was until recently. So, hang on. Slides aren't changing. Here we go. So, basically, my group is mainly based down at Plymouth Marine Laboratory. And I had to come up with some words to sort of justify what we do. And these are the words I came up with. So I'll read them to you now, even though you can read them yourselves. But basically, we work with an awareness of the global political landscape regarding energy, food and water. And we act as a regional, national and international focal point for the innovation and development of algal-inspired processes and solutions. So basically what that means is everything and nothing. I feel free to work on anything that's algae related that we can tie in with energy, food and water, which is pretty much anything if you think creatively enough. So the slides I've put together, I've tried to sort of make sense of my career and what we've been doing in and around algae. And this was a slide, or the next two slides really, the slides I put together for a different talk on imposter syndrome. This is something that I sort of feel I suffer from. And you'll probably see that in my as I go through all the slides, the sort of the areas that I've covered over the years. I know a little bit about an awful lot of things, but not a lot about most of the things that I work on. So I really do suffer from imposter syndrome. But like I said at the bottom here, I am getting better. I now consider myself a survivor of imposter syndrome. And when I lecture on imposter syndrome, I find that the most ironic thing about my life and career, to be honest. I think I'm an expert on imposter syndrome, which is hilarious, really. So this was the diagram that I came up with when I was discussing imposter syndrome. And right back, the then and now, I had a very clear vision of what I wanted for my career, which was to work on microalgae and viruses, academic. And it should have been a straight line and very straightforward. But what I found myself doing was constantly diversifying and moving into new areas. And at each point, I sort of suffered from imposter syndrome. So what I'm going to show you today is, I guess, the arrowheads of where we've ended up after some of these routes. It's quite a crazy career at times. We've covered a lot of ground. So I'm going to start off with, this is where I should have been and should have stayed, I suppose. So I used to work on the copper viruses, giant viruses that infect Emiliana huxley. So you can see in the picture of the culture on the left-hand side, a nice sort of golden glow to it, and on the right-hand side, it's all chalky. So when this algae dies following virus infection, it releases loads of calcium carbonate liths that it makes, and these liths things. Over geological time in the natural environment, you get structures like the White Cliffs of Dover. So I guess this is the first link to the GSI. So I should say that I'm a recent addition to the GSI team. So I've been trying to look at links to what I can offer to the Institute. And I guess this as an academic is one of the main things. I didn't know whether it was, I'm not really into all the claw hypothesis and the anti-claw hypothesis. I guess it's a bit like the government guidance at the moment. Is it a negative feedback loop or is it a positive feedback loop? I can't quite work out what the score is with EHUX and what it's considered to claw yet. But that's where I was. The problem with working on, well, anyone will tell you working on algal viruses is very little money in it. So I've had to diversify my funding. And the first time I did this, I turned to the dark side and applied research, is we started using our knowledge of viral infection to look at industrial processes. So the idea was, could we use viruses as a cheap, an energetically cheap and efficient way of breaking cells open to get the lipids out? And we worked on this for a few years with a large multinational oil company. And the main insight that I actually got from this was not that viruses were fantastic for processing biomass at all, but it was actually more that the biology wasn't the limitation. It's actually the scalability of the downstream processing. It was more of an engineering limitation that was sort of inhibiting biofuel production from algae. So that was quite interesting, as well as being lucrative research. Then we started looking at downstream processing technologies. So we ended up developing this thing that we call the vortex bioreactor. So the diagram in the middle of this slide sort of epitomizes the vortex bioreactor. It's not complicated at all. It's a tube with a propeller in it, and you turn the propeller on and you get a vortex in the tube. So it's exactly the same process that you see when you pull a plug on a sink, in a hurricane, even in galaxy spirals, you know. So what you get in the vortex is a really intense mixing zone. And our idea was, could we use the vortex to do biochemical conversions? So it's a very efficient way of bringing molecules together and allow conversions to happen. So the idea was we put algae in on the left-hand side in a culture. We whip them up into a vortex in a continuous processing manner, and then we'd be able to do the transesterification and get the membrane lipids out. And a really nice bonus of the vortex bioreactor is all the light material is ultimately thrown to the center after the intense mixing phase. So you could use a manifold to suck out the lipids in a one pot, one step process. So there's about 16 or 7 different technical challenges in doing that, from going from algal culture to algal oil. We managed to meet every challenge, but not in a line. So ultimately, although we got really far with this technology, it wasn't particularly great for biofuels in the end. But what it did do was, I mean, we were working on a system of about 6 to 7 liters. So what it did do is it highlight our massive inability to grow algae at the time. So what we worked out was that we really, I'm getting ahead of myself there. We did need more and more biomass and more capability in terms of engineering, in terms of rapid prototyping. So as we were working on the vortex bioreactor, we were changing things like the impeller design and speed that we were running at. So initially our system was running on a brass propeller that came from a model boat. So then we started going down the 3D printing route. So I bought 3 or 4 3D printers, and then this gave us the capability of basically printing a propeller every half hour or so. So we could run different propellers and vanes in the vortex bioreactor and optimize the conditions. So other things as well we did, T-Rex skulls, protein crystal structures, little microscopes. And here's something that it's very difficult giving a Zoom talk over this, because normally people laugh, and I'm hoping that you're out there laughing. But basically, here's a bit of a hint for all you budding romantics out there. Never give your wife a 3D printed dual colored ring for Valentine's Day, because quite frankly, the comments I got on Facebook when she put it on there were terrible. But yeah, that's a joke that maybe is not working over zoom. So yeah, we also got into 3D doodling as well, which is almost like freestyle 3D printing, additive manufacturing. And although I did a lot of playing around with this, it's actually really good from a learning perspective because you get to learn how plastics work. After just a few hours, you know how plastics blend, how you can sort of merge materials together. And this is stuff that I'll come back to later, and you'll see that we're exploiting that now. So as I said earlier, running the Vortex bioreactor, we're constantly needing biomass to run. So each run had 6 or 7 liters in it. So if you wanted to run 3 or 4 experiments a day, you do much larger cultures. So we we tried converting bioreactors that we already had around the lab. So you can see these in the top left-hand side with just normal chemostats. And we started building our own bioreactors. So the ones to the top right are our first early efforts with little bag systems, biocoils, and this beautiful helical. Oh, hang on. Did I disappear there or something? Hello?
Sorry, your microphone was sort of cutting in and out, so I thought it might be an internet thing. So I tried to turn off your video, but that didn't seem to help.
Oh, okay. Did you miss all of that?
I think we can hear most of what's going on. It's just every now and then it goes quieter.
Oh, okay. All right. Just shout at me then if you need me to repeat anything or anything.
So I thought you having the video and people can try and lip read.
Okay. All right. So yeah, we found ourselves sort of modifying and building our own bioreactors then. And the bottom left was our first commercial system that we started selling. So these are just bubble column systems that we started off using ourselves to generate our own biomass. And then every time someone came to the lab, they wanted to buy them. So I ended up selling them to colleagues and friends and then replacing them. Ultimately, we then ended up with a system on the bottom right, which is a 250,000 pound tubular bioreactor that's pharmaceutical grade. So I designed all of that myself, which was quite an undertaking for someone who's just a molecular biologist by training. So that was quite good fun. And for your info, it's not always expensive technology that we get involved in. These are just bag systems in buckets. They give us a couple of 100 liters of volume. So we take a pretty practical approach to sort of cultivating algae. This is where we're at the moment. We've got about 5,000 liters of cultures growing at any time in my labs, mostly in these tanks. So we're doing a lot of sort of genetically modified strains as well as natural ones. So I'll come back to that later as well. But our ultimate goal was algal goodness, I suppose. And we were constantly getting green and brown and golden pastes, and we also started using the cupcake as a unit of algal biomass because those silicon cupcake holders are really great for putting algae in. You can stick them in the freezer and stuff. And we've become pretty adept at sort of transporting green powders around the world now. So I'm almost as talented as a lot of the drug runners, I think, but legally, of course, and with paperwork. So after sort of starting off working on algal viruses and then dipping into biofuels and things like that, we found ourselves being asked to test people's systems all the time. We developed a reputation as sort of technologists rather than biologists. So people started coming to us with their systems, asking us to either improve them, test them, or develop them with them. And this was a whole new strand of research that actually became quite lucrative for us. So, for example, we worked with a company called Enlightened Designs who came up with a flat panel system. So if anyone's down at the Penryn campus, in the middle of the car park, there's a shipping container that's actually got this bioreactor in it. It's a very productive system, but the problem is gravity absolutely wrecks it because the flow rate is so low that the algae drop out at the bottom. So this is actually a system that we're developing at the moment for use in zero gravity environments on the space station and stuff. So there's a lot of opportunity for algae for remediation of waste products in space and things, and producing oxygen as well. We also developed a bag system with Algadix, the most awful company name I've ever worked with, to develop a floating bag system for offshore use. The beta barrel was literally based on a beer barrel brewing kit, and that's for domestic algal production, so things like spirulina and things like that, and Dunaniella that people can eat. We're also developing a few different systems with Varicon Aqua at the moment, but I'm under confidentiality agreements with it, so I can't discuss too much of that. But possibly the thing that the biggest surprise was when we delved into the sanitation sector as technologists. So I mentioned earlier the vortex bioreactor and all the different parts and components that we were trying to align to make biofuels work. And one of those was, could we take a cell and break it open simply in the vortex? So one of our controls was actually E. coli. And we played around with E. coli and various chemical, biological, and physical ways of breaking it open. And we hit upon some copper powder that we got off eBay. So we put copper powder into the vortex bioreactor, and we find that it killed E. coli within 10 to 15 seconds. The problem was we then had copper powder in 6 to 7 liters of water, so we had to sort of get it back out again, which was a bit of a problem. So we had to filter all our material and stuff. So we actually thought, oh, we'll just embed it in some alginate, some seaweed extract, because we work with alginate all the time. So we ran our experiments with copper embedded in alginate, and instead of killing E. coli within 10 to 15 seconds, which we were really happy with, we were killing it almost instantly. So this stimulated us writing a 2-page give me some money document to the Gates Foundation. And we found ourselves funded in the Reinvent the Toilet Challenge. So what we basically developed was a very cheap and easy technology for sanitizing waste water that's pathogen rich. So we actually went through 4 rounds of funding with the Gates Foundation. So the top left picture is me presenting the technology in Seattle. So the corner image, the top left, is actually Bill Gates' office, and the top right photo shows Bill Gates walking by the vortex bioreactor. You can see my head over the guy's shoulder who's pointing. And this photo was taken immediately before the massive security risk I created when I decided to step out and talk to Bill Gates when I wasn't on the rota. But the guy in the orange tie is actually now the King of Holland. He laughed so much about it that he actually stayed for 20 minutes and had a chat with me because he thought it was the funniest thing he'd ever seen in his life. Well, we actually took the vortex bioreactor around the world. So it's been tested in Brazil, Uganda, Hawaii, even though they're not a developing country, and it's just one of our co-developers was there. And I personally spent a week in a sewage treatment plant in Pune in India testing it. The long story short is it works absolutely fantastic. We can test it out with, I've kept this presentation data light, but basically if you look at the 2 graphs in the middle of the screen, as we add in, if you put E. coli in the vortex bioreactor, it actually grows quite nicely. And then we add in our alginate copper beads, the numbers go down to 0 almost within seconds. We can do that with 1 million E. coli per mil up to 1 billion E. coli per mil. We sort of tested it. And the graphs on the bottom right are where we compared it with UV sterilization, which is the sort of the technology that has probably come up against in terms of function. So what you find with UV sterilization is you need to put more and more energy in, the more discolored the liquids are and the more solids that are present. So you can see as you progress along the x-axis that the efficacy decreases and the survival decreases with UV sterilization. So for reference, the vortex bioreactor is actually plotted on the same graph, but they kill everything no matter what the solid's losing. So those are the spots along the x-axis that are all on 0% surviving. And it also kills Deinococcus radiodurans, the hardiest bacteria known to man. So that's the thing that grows on the inside of nuclear reactor cores, whereas we kill it almost as rapidly. Does take a little bit longer. I think we're up to about 20 seconds for Deinococcus, but it is practically indestructible. So working on the Reinvent the Toilet program did give us a lot of insights into deploying solutions that you come up with as scientists in a global setting. And what was really interesting for us was we found ourselves really useful to everybody else on the program, because they were all reliant on doing something with the solids, basically, dewatering and drying out. And no one had dealt with the water side of things, which was why we managed to I think we sort of parachuted in at the right time and place. But it did give us this sort of insight that dewatering and drying is a massive opportunity in terms of industrial processing and doing things at scale. So we started looking around in this area as well. And we were finding this with microalgae as well. So with microalgae, they grow fantastically well. But at the same time, there's so much water associated with them. Harvesting the algae is a real nightmare. So the reason why they grow well is because they're surrounded in water. The reason why they're a nightmare to harvest is because they're surrounded in water. So we started looking at electrochemical separation. So we were looking at the sort of best efforts on in the published literature. And we managed to develop a way of harvesting, these top cultures here were exposed to between 5 and 6 seconds of our electrodes. And you can see how beautiful the separation is there. And we also sort of started working out novel additives to improve the stability of the foam separation as well. So bottom right is quite it may not look much to you guys, but actually that algae on the top there has got the consistency of Angel Delight. And is actually fantastic to work with because you can sort of skim it off really easily in a robust way. So it also stabilizes the material as well. The reason it looks like Angel Delight is we actually used milk powder there, which was actually quite novel. It doesn't sound much, but whilst we were running the chemical system, I got the guy who was running it to reverse the electrodes just to see what would happen. And what we noticed that with a little bit of cell death, the cells would release their contents, and actually the dead cells would actually help bind up the living cells. So then we started looking at binding agents and came up with condensed milk, which is actually really cheap, very readily available. So it's a really cheap and easy way to harvest algae. So at this stage, we were, making biomass. We could harvest biomass. We really had to start looking at what we were going to sort of do with the biomass. So this is a project that we have funded with the Newton Fund and some Mexican partners. So we went about isolating microalgae from our local area. So these are actually looking at, we started looking at ways of how you can use the growth of algae as part of a service. So algae are often sort of suggested as ways of remediation applications and, like heavy metal toxicity and things like that. But you can't actually do anything with the biomass at the end of it. So we started looking at ways of combining all of this. And then we discovered a technology called hydrothermal liquefaction. And that sort of really helped us sort of crystallize these ideas. So hydrothermal liquefaction is a really cool technology. So it's basically it's high pressure and a high temperature in a contained environment, and your biomass is actually wet. So you can do it with about 20% solids and use water as the solvent. So there's no drying there, or very little drying. And you get 4 main products out. So you get a gas phase out, which is mostly CO2, which you can recycle to grow algae if you need to. You get an aqueous phase, the water, which has all your nitrates and phosphates in it. You get a solid char, which is mostly where all your metals go. So that's where we were interested in this initially. And you also get an oil out, which you can upgrade into diesel and bio oils. So we first got funding for this from GW4 on the Avarice project. So we started off life down in Falmouth, where we were looking at acid mine drainage, binding algae to the acid mine drainage, removing the metals, so the algae would absorb the metals, and then converting the algae into oil, which would then subsidize the sort of cleanup process by running all the pumps and things. So, for example, the site down in that one site down in Falmouth where we started, it costs the taxpayer £5 million a year to run. They don't get anything back for that. So our idea was if we could use algae, you'd at least be able to produce fertilizers from the aqueous phase and oils for sale, and actually maybe bring the cost of remediation down. So then we started applying that concept globally. So we had a really nice project funded through the GCRF with some Vietnamese partners. And here we were looking at lakes in and around the Hanoi region, which are absolutely rammed full of microalgae and completely toxic in some areas, but also loaded full of heavy metal as well. So our main partners on this one were Petro Vietnam from industry, and they were really interested in the oils that they could get out. And this was a really cool project, actually, whereas we tried to sell the concept of using the lakes as bioreactors. And so you don't have a sort of cost of growth, you just have a cost of harvest. And that's why we were developing the electrochemical flocculation as a cheap harvesting tool. So that's been quite an interesting one. But the problem is over the last few years, the oil prices have plummeted. So the drivers from industry there are just not there at the moment. So while we were doing that, we were sort of cultivating an awful lot of microalgae, which would take us weeks or months to generate. Whereas we actually found that if we wanted some test biomass, we could just pop down to the seashore and grab some seaweed and grind that up. So it was much easier to harvest, and we can get a lot more biomass very quickly. And because my kids got involved, I also had free child labour for collecting it, because it's not entirely free. You don't have to bribe them with ice creams. So we started putting seaweed through hydrothermal liquefaction, and the results were actually pretty cool, and the conversions were fantastic. So I found myself working on seaweed. So this is about 3 or 4 years ago was my first sort of foray into the seaweed area. And this opened up a whole load of opportunities. So I didn't know anything about seaweeds. So I just bought a simple book and then went sampling. So to all you sort of students out there, if you're ever worried that you don't know anything about what you're doing, I've built around £1 million worth of research funding off knowledge that I've got from one Seaweeds of the UK book. So it's as terrifying as it is sort of liberating to know that you can do that. So we started off in my lean-to on the back of the house, collecting bags of seaweed. You can see Gracilaria here spelt badly on the label. And the kids have been helping me with this over the last 3 or 4 years. And they're now acknowledged on 6 papers, which I'm pretty proud of, actually. So they work really hard for me. I also built a lab for them so they could do it properly. So if anyone's interested in the stuff that my kids have been up to, you can check out bluemicrobe.co.uk or hashtag the Allen Lab on Twitter. So this is a lab that I built on the back of my house when we were undertaking a refurbishment at PML, and this lab was being thrown out. So I took it home and built a new lab for them. And this is my local beach on Broadsands. So this is where we started with some of our experiments that have been running in both the lab and at home. So you can see the beach here is covered in algal lactuca, the green seaweed. And this is if any of you saw the Beijing Olympics when they had to sort of trawl the whole harbour prior to the sailing contest there. So it's basically, these seaweeds just basically blocked up all the seas in the area. So these are algal blooms all over the place. You also get it around Normandy and in the Channel Islands as well, and on my local beach. So you can see on the left-hand side where it's gone white, it's become bleach. So this is really interesting from a fuel perspective. So the older it is, the lower the sulfur content. So as this degrades, it gives off the gas dimethyl sulfide, of course, which, so when you convert that biomass into oil, it's got a higher value when it's older, but you get less of it because a lot of it is broken down. So it's a trade-off between the value of the oil and the amount of biomass you get. So this is what the experiment bottom left was trying to achieve, as we were looking at under lab conditions how it degrades and the sort of the sulfur content of the fuels that were coming off. But this experiment didn't actually work because it was in a lab. So I thought, I'll take this away from the kids because you know, the guys in the lab should be able to do this better. But the problem is there's no weather in the lab, so there was no degradation. It just sat there like a pile of green, stinky stuff. So it actually took me going back with the kids and doing it in my garden on the raised beds, which my wife wasn't best pleased about. So I had to engage with some of my kids' friends because we needed more and more biomass. So it cost me 4 ice creams, this experiment. And then we just tracked it over a week or two of degrading. And I was then taking the seaweed into the lab for conversion. So I'll probably publish this in the next few months when I get around to writing it all up. So it's quite an interesting piece of work there. So as the price of oil had dropped as well, the drivers for fuels were becoming less and less apparent. But the problem with seaweed was becoming bigger and bigger and bigger. So we really got interested in what was happening in Mexico and the Caribbean, where they're getting absolutely shed loads of sargassum washing up on the coasts. So we thought, well, maybe we could ignore the biofuel product for now and look at that aqueous phase. So we came back to sort of fertilizers, but instead of the sort of bioactive ones that we'd been developing through the Neptunus brand, we were looking at crude bulk ones. So it is a different market, but we already had the right partners in place. So this is the Phycomex UK project, which is Newton funded and GCRF funded at the moment. So this is a great little project. So we're basically using the seaweed in Sargasso, Sargasso seaweed in the Mexican coast to develop a solution to convert it into fertilizer on an industrial scale. So when you think about the scale of activity here, I think last year, there was like 9 to 10 million tons of seaweed hitting the beaches. So what these guys are generally doing is digging a hole and putting it in, which doesn't solve anything. It just comes back. So what we're trying to do is actually come at it from an industrial perspective and develop the business process for that. Plastics is another big issue. So coming back to this, you know, it's not pure seaweed. There's plastic mixed in amongst it. You can't ignore them if you're developing industrial processes. So we've been looking very closely at plastic and degradation in the natural environment as well. But they are also, although they are a problem, they are a massive opportunity because they are so energy rich. They are just carbon polymers after all. So we are interested in remediation. We're also looking at how they degrade, and we're also interested in looking at new plastics as well, degradable ones or bioactive ones and novel composites. So this is a really interesting area, and you know, I was alluding to it earlier when I learned my interest in this was kindled when I was playing around with the 3D printing and the doodling. I thought there's a massive opportunity here. So this was some work that we published last year, whereas we can basically convert plastics alongside the seaweed and convert it back into oil and fertilizer, which is kind of cool. So if you put plastic straight through a HCl rig on its own, you just get plastic out. But if you put plastic in alongside seaweed, the seaweed catalyzes its conversion. So this is a really cool technology for remediation of plastic from the marine environment. So one of the, you know, we all sort of separate our plastic and you know, send it off for recycling every week, but most of the time it isn't recycled. It just gets piled up because, you know, the recycling facilities just aren't there, or the plastic is contaminated in some way. The great thing about HTL is it's feedstock agnostic. It doesn't matter what the state of the plastic is, whether it's got a biofilm on it or if it's in bits or anything like that. It just converts it all as is. So this is a really cool technology that we're quite hopeful of. We're also interested in degradation and the activity of plastics in the environment. So this is some work we did with some of Tamara Galloway's group, where one of my other sort of roles is I work quite closely with the physics department in Bristol University, which gave me access to one of 3 versions of high-speed AFM in the world. So there's only 3 of these pieces of equipment in the world, and I own one of them in our lab. It basically gives us a nanoscale resolution for material science, but we've been applying it to the life sciences. But basically what you can see on the left-hand side is a virgin piece of plastic, and then on the right-hand side where we've run some antibiotics over it. So you can actually see the antibiotic molecules binding to plastic surfaces. We can also use this technology to look at plastics degrading in real time. One of the scariest videos I've ever seen is tooth enamel with orange juice on top of it, and you can actually see your teeth dissolving at the nanoscale in real time, which is just horrific. We've also been looking at plastic algae composites as well. If any of you are really rich and have some Vivo barefoot shoes, I have a free pair that they sent me to cut up. Basically these shoes are blended very much like Crocs, but blended with microalgae as a greener material alternative. So on the bottom left-hand side here, you can see the plastic filaments. On the bottom right, you can actually see an algal membrane. So we're just sort of working out how these sort of composites come together and blend. So I'm going to leave it there. This is a massive team effort. I've worked with so many people over the years, all around the world. But Bath are the guys that have done all the HTL, which I've featured a lot of today. And I've worked with industry partners as well, so many of them, but these are the main ones here from these slides. And thanks to all the funders who funded all this stuff, and mostly to Team V members and friends, past and present, and the kids for helping me out. And if you're interested in all this stuff, look on my Twitter page, and there's always stuff on there. And apologies for the random nature of this talk, but I wanted to sort of show you some of the stuff we're doing and why we're doing it and how we've got there. So I'll leave it there for now.
Great, thank you.